Morning, and thanks for joining us for Ventilate Rate Part 2. This is part 2 in a 3-part series that we're doing on ventilation, on residential ventilation. And this part specifically focuses on distribution controls and maintenance, so distribution systems like ducting systems. I am Karen S. Bushy. I'm a senior engineering consultant at VEIC, and I have 10 years plus experience in designing and verifying ventilation systems, first for more high performance projects, and then recently for the Efficiency Vermont residential new construction program, where we've had balanced ventilation as a requirement for the past, I think, at least 6 or 7 years. And then I'm presenting today with Mark Toth, who will introduce himself.
Hi, I'm Mark Toth with RST Thermal. We're a manufacturer's representative firm. I have been in the HVAC industry in one capacity or another for the past about 35 years. And I've been with RST Thermal for 13 years. The company is based in Fall River, Massachusetts. My territory is Vermont and New Hampshire. I do live in New Hampshire. Spend about half my working time in the state of Vermont. So I'm pleased to be here with Karen, and hopefully we can answer some questions for you today.
Okay, there we go. This slide is really just to say that there's content in this presentation that includes some code language. We're going to be talking about the Vermont Residential Building Energy Standard, and the official code language is actually copyrighted by the ICC. And here's a little bit more about the code. It's updated every 3 years, roughly. And the most recent version of it went into effect this past July 1st. And that has a section that we're going to be talking specifically about, the section that pertains to ventilation and the big change that happened with this past update, which included a requirement for ventilation. I'm hoping to get this slide deck out to all of the attendees for this presentation, and anything that's like highlighted in blue with underlined is a live link, so you can actually go right to there and find the latest publications for each of these things. So it'll give you the latest code publication. Just to note that there is a difference between the official code book with the official ICC language and the RB's handbook. If you have any questions between the language of the two, always defer to the official code that's shown in green in this slide. And the handbook is meant to be more as a guide to sort of help explain the official code language. These are the old 2020 versions. Unfortunately, the 2024 versions are not out yet, but I expect them to be out very soon. So as I mentioned, this is part 2 in a 3-part series. Part 1, Mark and I presented on August 29th, and the recording has not been posted yet, but it should be soon. But in the meantime, I found a residential ventilation code training by Steve Spatz, which you can get to through this link right here, right here. And it covers a lot of the same information if you're just needing to size a system right away. Today, we're going to be talking about distribution controls maintenance. And for part 3 on October 17th, we'd like that to be really a question and answer session where we do a little bit of review, but really dive into those questions that you guys have that maybe we didn't cover or you want to cover in more depth. So I'd ask that you send any questions or topics that you want to cover in that to my email, ksbushy@veic.org. And then we'll be happy to put together a session. I'm thinking that one on October 17th will be at noon instead of 8:30. So just keep that in mind. That's not verified yet. It'll either be 8:30 or noon. Today, this is what we're going to be covering: system design recommendations, distribution systems and registers, controls and commissioning, and maintenance and troubleshooting. And these are the objectives that we hope that you will take away from today's training. Just a quick slide showing some abbreviations, and sometimes I turn these into their own words. So if you hear me say RBs, I'm talking about the residential building energy standard. CBs is the commercial building energy standard. Different people say these different ways, so don't let that throw you. EVT, Efficiency Vermont, and of course today we're talking about ERVs and HRVs, energy recovery ventilators and heat recovery ventilators, and the efficiency metrics for them, which include SRE and TRE, the recovery effectiveness, And ASHRAE can turn in, the term ASHRAE is stands for American Society of Heating, Refrigerating, and Air Conditioning Engineers. We don't talk about that a lot today, but we did talk about in the first session. FIAS is how I say the Passive House Institute US. There are some metrics for figuring out total airflow through the Passive House standard. So that's why that ended up in here. And just to note the measurement units for static pressure, inches water gauge or water column, or sometimes I use those interchangeably, even though maybe they technically aren't the same thing. Also just use static pressure. And feel free to correct me, Mark, if I'm saying things wrong as far as like the industry standards go.
No, it's fine. We'll keep going. That's fine. And again, today the next session is question and answer, but feel free to ask questions today also as we're going through this.
Oh yeah, thank you for saying that. We are fine with you interrupting us with questions as long as it
Actually, a
doesn't
few
get
questions would be good to keep us all tied together and intact. So feel
and
free.
addressing the things that you want to learn about. So again, this is a very, very quick recap of what we talked about in part one. We're talking about the fact that with this new code update that into effect on July 1st, there is a requirement for all new residential construction to include whole house balanced ventilation system. And the code efficiency requirements are a minimum of 70 sensible recovery effectiveness. So that's the thermal efficiency of the unit, basically how effectively it's transferring the heat from the two airstreams, from one airstream to the other. And 1.2 CFM per watt, which is the motor efficiency, which is really how efficiently those motors are moving the air. That's a very simplified version. And I wanted to distinguish from that what you're seeing in this slide, which is Efficiency Vermont's qualified products list. If you go to this link or on our, I think it's market products section of our website, you can go to whole home ventilation and search for qualifying units. And these units have different criteria than the code, what I just mentioned of 70 SRE and 1.2 CFM per watt. The metrics that we're using here actually are 75 SRE and 1.7 CFM per watt. And also these are verified to be cold climate rated down to negative 13 degrees Fahrenheit. And the reason for this is because this list are the units that qualify for additional incentives for Efficiency Vermont's residential new construction program. But if you're looking for a unit that is more efficient than the just typical code minimum, then this is a good list to use. And if you're an EEN member or building a new home, then this is a great opportunity to get some additional money for your ventilation system. I also wanted to mention, I meant to mention on the last slide, that if you're just looking for the code minimum equipment, what we talked about last time, in case you weren't there, was looking that up on the Home Ventilation Institute website, HVI. If you go to HVI ventilation, just search HVI ventilation, I'm sure it'll come up and you can search there and it'll tell you just on the landing page what the efficiency ratings of the units are. So I'll let Mark tell you about
So we're going to cover a lot of different things today, but we're going to be talking about ERVs and HRVs. And just so everyone's aware, there are multiple brands out there. The list on the left here, I don't need to read it to you, but those are some of the more common brands that we're seeing out there in the marketplace. And, it kind of like everyone says, well, which is the best unit? And I guess it would depend on your particular application, whether it be ERV or HRV. And as far as the brands go, really everyone is making decent equipment now. No one's really making anything that we're seeing on a day-to-day basis that's really junk. I mean, if it meets the efficiency Vermont standards and meets all these criteria that we have, it's going to be a fine piece of equipment. There's definitely differences in design, in construction, and installation techniques. You can see them from the pictures here. Some come off the top, some are off the sides, some have smaller duct connections like the Zender unit there. There's a whole ducting system. And also here, there's a very large range of pricing that can go on. You can see a unit here on this picture that might be $1,000. One of them might be $7,000. It's a huge range there. And that definitely does not always indicate that a unit is better than another unit just because it costs more. We're also seeing some of the other units on the bottom, the Serve, the Minotaur, the Epoca, I guess it would be called.
Yeah,
These
Epoca.
are ERVs, HRVs that have heat pumps built into them. So they're kind of like a multi-purpose unit. I haven't gotten involved with those a whole lot, but I've heard some people love them and other people can't stand them. So it's just another type of product that we're really not going to deal with in this presentation, but just be aware that they are out there. So you can go to the next one. So ductless options, Karen?
So yeah, these are some of the non-ducted systems that we're seeing, some of the names that we've seen out there. We wanted to say about the ductless units is that they do serve a purpose, but we're seeing that because of the fairly low flows that are offered by these pieces of equipment, they work best for just single room solutions, like an addition perhaps, or very small homes that have few interior walls and are very open. Otherwise, it really can add up with the number of penetrations through the wall, the number of pairs of units if you have the single hole type, and you're kind of like uh, um, not getting the benefit that you intended to get in the first place with these units. So they are good for certain applications, but
Right.
in general, for new construction, single family homes or even multifamily, we're finding they're not the best solution.
Right. It definitely has its place, but not as a whole house ventilation system in most cases. I did see someone comment about the other ones I mentioned with the heat pumps and integrated, and you can do some research on those. Again, we're not going to really get into those today, but what I'm finding is that they're not always that great of a heat pump and also not that great of an ERV, HRV. Kind of like you get a little bit of both, but not really good at either one. So
Yeah, and they're all different. Like they're
yeah.
very different, each of them. So we're happy
And
to
and at this
talk about
point
them.
they're kind of very how would you say, like niche products. They're not commonplace. There's probably 100 or 200 normal ERVs, HRVs put in for every one of those. They are out there. They are making a little bit of a scene, but they're not very common.
Mhm. All right, we're going to move on to system design recommendations. I'm going to let Mark take this one.
Yeah. So features to look for in an ERV, HRV. I guess there's the bullet points there really describe everything. So how quiet is it? That's very important because we want the people to run them. The last thing we want is a noisy system where the homeowner is going to shut it off. And there's also different designs there. You can have a 24/7 low speed with a boost. You can have intermittent operation. The units themselves, some of them are insulated better. Some of them have heavier cabinets. Some of them have quieter motors. Just the whole package. You got to really look for the one that is going to be specific for your application, what's going to be best. But definitely having them be quiet is extremely important because if they're not, the homeowner is going to shut them off and not have proper ventilation. Controlling the units, there are multiple ways to control units. As you can see here, you have all kinds of sensors. You have VOC sensors, you have CO2 sensors, you can have motion sensors, you can have timers, you can have on demand switches. There's a lot of different ways. There's no one way that's best for every application. Obviously, each application has its own specific needs, and we try to fit the application with the control because when you have one way to control it, it's really good for a certain situation, but another situation is not good at all. So just to say, if you're looking at CO2, CO2 is a great way to control areas that have a high concentration of people. Say if you had a big home and someone was building a home that they were going to have a room where they're having exercise room or they're going to have a room where they're going to have people over all the time to hang out and do projects or whatever it's going to be, or it's a meeting room, that kind of environment, CO2 is great because you're going to get CO2 spikes and you're going to ventilate it. But CO2 for an entire home regular house would not be normally a good way to do it because you need to ventilate for a lot of other reasons besides CO2. And you may never reach the CO2 level to trigger that sensor, depending on how the home is being used, how many people are there, how long they're there for, that sort of thing. Also, there's a lot of things about motion sensors that are good and bad, but we'll get into that as people have questions. Filters. So most of the units come with a MERV 8 filter in them. Just be aware that some units you can upgrade depending on the manufacturer. You can add up to MERV 13 or higher filters into the system. Others will not let you do that. It depends on the strength of the motors that are in there and how powerful the motors are, if they can overcome the static pressure of the better filters or not. So if you're interested in upgrading filtration, definitely look into that if it's possible for the unit you want to choose. Also, my thought on that is that you only really need, there's only any reason to increase the MERV rating on the incoming air filter from the outdoors. There's absolutely no reason to upgrade the filter on the exhaust side because you're just putting stuff outside. It doesn't matter what we're exhausting from the house. We don't need to filter that better. The only reason that filter is there is to keep the core clean. We're not worried about cleaning the air that's going outside of the house. Defrost, different units work differently. HRVs all have a defrost, which means that in cold weather, seeing that that core is made out of either plastic or aluminum, on a cold day, it's gonna condense and freeze and eventually freeze shut, basically, so the air can't get through it. So it needs to have a defrost system so that it has a way to thaw that out. Some do it by a heater, some do it by recirculating indoor air. There's multiple ways, but it's going to have a defrost. And when you have a defrost, it means you have a drain because you're going to drain water out of the unit. So you now need to have a drain. On the ERVs, generally, ERVs don't have a defrost cycle that has water, but some do. So it's not a blanket statement. There are some ERVs that need a drain also. The one that I'm most familiar with, and several that I'm most familiar with, do not have a drain. The company I work with mostly has no drain. Units can go in any position at all. There is no defrost cycle because the core does not freeze even down to minus 25 degrees. So really look into the technology of the unit that you want to purchase to make sure it fits your needs. And, this drain thing is a big deal because when you're building a new house and you're installing an ERV or an HRV, and at the last minute you find that you have to have a drain line from it, and there's no drain in your basement where you're going to put it, that becomes quite a bit of an issue sometimes. So just take everything into consideration when you're looking at the units. How quiet is it? How are you going to control it? The filter options and the defrost. So look at the whole picture before you make your decision. So go ahead. Locating the unit in the home. A couple of pictures here for you. One of the most important things when you're going to locate it in the house is to make sure it's in an area that's accessible. If you look at the first picture there, kind of in the middle of the screen, they've installed the unit and then a ceiling wall or something was built there. So that door cannot be opened. How are you going to change the filters? How are you going to service that unit? That is a very bad location. The one up in the rafters, not the greatest place because once again, it's kind of difficult to get to. A lot of places you're going to have to get a ladder to get to something like that. Making it easier to get to is going to make sure that it gets maintained properly and checked out from time to time, and people are going to take better care of it. The one in the basement here, it looks like that one's going to be very easy to get to. You won't need a ladder. You're not going to have to move a wall. It's going to be put into a place where you can get at it easily. And this one here, yes, she has a picture saying that this exterior intake is way too long. And I think that would depend on the unit. And obviously that if that is the intake, it needs to be insulated no matter what. So that is not, maybe that's in progress of being installed, but that incoming airline definitely has to be insulated. And we'll cover more on that later on why that has to be done. So go ahead.
You have a quick question here, Mark, going back on the defrost cycle. William was curious if the ERV versus HRV material allows for condensing.
So in HRV, that core material is either going to be plastic or it's going to be aluminum. So an HRV, as we covered last time, does not transfer any moisture in the system at all. So when you get condensation, it's going to freeze, or just condensation in general has to go out through a drain. With an ERV, some of the ERV manufacturers have core materials, like the one that I'm most familiar with is called a hygroscopic resin. It does not condense. It will transfer some moisture through the material of the core so that it never actually produces water and it will not freeze. So how much water does it, how much humidity does it transfer? That's all variable depending on the conditions. There's a sliding scale as far as what temperature is it outside, what temperature is it inside, how much humidity is inside, how much humidity is outside. Whatever it is, this unit tries to balance humidity rather than take it all out or bring it all in. We're trying to create a comfortable environment, and it will not condense. It does not make water. So that's just one brand that we're talking about. But we can dig into that later a little bit more if you like. But very big difference between ERV and HRV and how they manage moisture, for sure. Intake hoods outdoors. So one of the things here mentioned is that we have to keep our intakes and exhausts above the snow line. So it says 12 inches above snow line. That's what we're shooting for. We don't really ever know where that's going to be. But we need to keep them above snow line because we can't have them get buried, because once they get buried in the snow, it's not going to work properly. Exterior intake duct, I mentioned that a minute ago about insulating that. We're going to have pictures later to kind of really get into that and talk about why that has to be insulated. So anyway, the biggest thing for locating in the home is make sure you can get at it. Don't build it into somewhere where you can't get at it or where it's going to get buried back in some corner and no one can access it, because they do need to be serviced. Not often, but at least every 4, 5, 6 months, you're going to need to get in there and change or at least inspect the filters. So move ahead, Karen. Filtration, MERV ratings. So we said most units come with a MERV 8. You can get down to MERV 6. You can get MERV 13. You can get HEPA filtration. It's just it's a rating. You can look at the little chart here on the bottom. It's all variable on what this filter is going to catch. Is it just going to catch bats and butterflies, or is it going to catch the PM 2.5 microscopic that you can't even see in the air, and anywhere in between? It's a sliding scale, and again, at some point, the static pressure of having that better filter is going to overcome the ability of the fan to move air through it. And any filter, as it gets dirtier, is going to restrict airflow even more. So the better the filter you get, the higher the MERV rating, you're going to also probably need to change that filter more often because it's catching more things and plugging up quicker. We have other options out there for air disinfection. So any filters that you're seeing, we're just filtering things out. We're not killing anything. We're just removing particles from the airstream. There's another product out there called Revive Air that we've just started working with. It's actually a unit that it's a filter that doesn't filter particulates though. What it does is it kills viruses, molds, and bacteria. And then you would have your particulate filter after that. So we're killing the actual viruses and it's bursting them into thousands of little molecular pieces. And then you need to have a very high MERV rating filter after it to catch those pieces. So we're not just now blowing, we'll call it dead material around in your air. We want to actually kill it and then take it out. But once again, in an ERV, HRV application, that type of filter is not going to be as important as it is in a system that's recirculating air in the house, because we have to remember, we're bringing in fresh air from outside. We're hopefully not going to have viruses and bacteria. Hopefully our intakes are going to be in a clean spot and we're getting clean outdoor air. Having UV lights and so forth in an ERV or HRV incoming air really doesn't make a lot of sense to me, because the outdoor air is UV treated by the sun, We have a huge UV machine out there treating all the air before it comes in our house. So it is important to clean the air coming in, but as far as that disinfection level and taking care of viruses and that sort of thing, that's going to be more important in a furnace type application or a recirculating air cleaner, that's not bringing in outdoor air. So bringing in outdoor air, we're really starting with the best air that we can start with as far as being clean. We just want to make sure we get those particles out of it that could blow around and create dust in the house.
So if you have a ducted heating and cooling system, there are pros and cons to integrating the ductwork of your ventilation system with that or not. We could literally argue both sides of the coin, and we're going to attempt to do that here. So for standalone systems, completely separate heating and cooling and completely separate ventilation, the benefits of that are you're able to right size the ducts for each application because the amount of air that you need for ventilation is so much less than you need for heating and cooling in general. So you're able to, use smaller duct systems for your ventilation and ensure that you're getting fresh air delivery to each of your rooms in your house and design the system for that. It's going to require more duct work and more space, obviously, for two completely ducted systems. And so that's one of the drawbacks, as well as the material that you're using to make those systems. And one of the big benefits that I see is that you don't need to run your air handler year round like you would in the other type of system. It's a much more efficient use of the fan because in theory, you're having your ventilation system run all the time, almost all the time or all the time. And that motor that's moving that air is a much more efficient one because it's a lot less air than the heating and cooling system. And I'll let Mark talk about the integrated.
So yeah, just to comment on the standalone, if you're building your house and you're going to use, say, heat pumps and non-ducted heat pumps, or you're doing radiant in-floor heat, then yes, you have to use a standalone unit because you don't have any ductwork in the house. That makes all the sense in the world. You need ductwork to move the air around. But if you're building a house and you're going to use ducted heat pumps or maybe a Unico high velocity or any type of ducted system, if the other opinion is if you have ductwork there already, why duplicate the ductwork? There's multiple reasons why not to duplicate the ductwork. There's the cost of duplicating ductwork, of materials and labor. There's the environmental cost of duplicating it, that you're using twice as much material. You're going to have a lack of space because you're going to use twice as much space than you needed to. So there's a lot of reasons why not to do it. If you have duct there already, I would argue to say use the duct that you already have, put your ERV or HRV tied into the return of the existing duct system, and that's one point you would not operate it 24/7. In that scenario, you're going to operate it intermittently. You're going to put it on a timer. So you're going to run your ventilation system, say, either 10, 20, 30%, 50% of the time. So say 50% of the time, you're going to be running the system fan on low speed in conjunction with your ERV, HRV. So you're going to be bringing air into the return closer to the blower, taking air out of the return closer to the return grill. So you're going to be moving fresh air into your system. As it comes into the system, it goes right into the blower, gets dispersed through the whole house at a very low speed. So you are now moving air through every room in the house because your heating system, your cooling system is obviously dispersing air through the entire house, where a lot of times with an ERV, HRV standalone duct system, you don't get everywhere. You have to pick and choose where you're putting and taking air from. But with the whole house ductwork system that's already there for your heating and cooling, you're pretty much going to cover the entire house with fresh air. It's just going to operate, so you're talking about using the system fan. Yes, you're using the system fan. Most of the system fans now are all ECM, so they have a very low speed to work in conjunction with the ERV, HRV. Yes, that costs a little more money to run that fan, but I think if you did the math on it, creating a whole nother duct system will be thousands of dollars, and integrating this, running that fan for an extra 20 or 30 minutes of every hour on low speed, that ECM fan, I think you're going to be at a very low electrical cost, and it would take you many, many, many years to ever reach the point of paying for the entire separate ducted system. So.
And Mark and I were talking about this before, how you have to know that you can't actually power off your HVAC system because it has to actually, if you turn the switch off, then obviously that air handler won't be able to run. So you won't be getting any fresh air delivery.
Right.
So that the unit
If
has
the
to
ERV
stay
was
on.
running without the unit running, it would just short cycle inside the ductwork, because you're taking air in here and pushing air out here. Without that system fan moving it through, you would just create a really short cycle in your ductwork. So, like as Karen said, if you shut the system down, you're actually then shutting your ventilation down also. But I would argue that most people don't shut their HVAC system off, especially today. Everyone's doing heating and cooling, and even when it's a day like say today, you don't need heating or cooling. You're not shutting your system off. The thermostats are leaving it off. So then when your ventilator comes on, it's still going to move air through the system as it needs to. But I would argue that most people are not actually turning their system off.
It's one of those homeowner education pieces, I think.
Right.
We're going to move on to distribution systems here. Just a note, a couple things that make up a good duct system. We're going to be talking a lot about distribution systems in this session. So you want to ensure that your ducts are within the thermal envelope. That actually is a code requirement. Make them as short as possible to save cost and to reduce static pressure. And low resistance, also reducing static pressure. Keep the system simple with smooth ducts and fittings and sealed. Low noise, so decoupling it from vibrations, both for the ducts and the unit itself, so that people use it and don't turn it off. Adjustable, so that you can adjust the right amount of air to each room. And mixing air for comfort. So this includes the selection and placement of diffusers, and how that air is diffused from the register, so it's not blowing directly on people and mixing with the room air. And also something that is tested and balanced and operating the way that you intended it in your design. So just a note about ducts inside the thermal boundary. This is a good graphic to show, you don't, in unconditioned attics, leave the ducts out of there. In general, especially in a lot, we're talking about new construction, there's always exceptions that can be made for existing construction, especially in a state where there's not a lot of oversight. You can get away with a lot, but in general, the best practice is to keep all of your equipment and your ductwork inside the thermal envelope. Some ideas for how to do that in new construction or even a retrofit would be to insulate in your rafter bays. That is an option for retrofit, actually, so that you can then have a place to put your ducts inside a thermal envelope. You can also build up like an inverted soffit up into the attic where you can install ducts. This is a very tricky thing to do well, I found in practice. It's very hard to air seal that box. It's not impossible, but you just have to really pay attention to where your thermal envelope and your pressure boundary is. The system that I like the best are the dropped ceilings or soffits, where you can, just do your finished ceiling flat all the way across and then drop down a corridor ceiling to have some extra space to run those ducts.
I'm seeing a lot of the conditioned attic spaces in new construction now with the spray foam. A lot of people are spraying the entire outer edge. So you do create a not necessarily heated and cooled space, but a in the thermal envelope space. So it's a
Yeah,
great
that's a
place
good
for
way to do it.
equipment.
And this is just a note slide to show how, the smaller, shorter, not smaller, but the shorter compact duct systems really are just as effective. And they save cost and they save energy because you're not pushing the air so far. And with some really strategic location of your registers and selection of those registers, so they're kind of throwing the air into the room and directing that air against the wall or the ceiling and not onto people, you can actually put those really close to the interior doors or, of the room and not have to bring them all the way to the exterior wall. And we're actually finding this for heating and cooling systems in high performance homes as well. That mentality of having to deliver out the exterior window doesn't necessarily apply if you have a very tight, very well insulated, and even triple glazed windows. You're not, it's not necessary to do that.
Well, the other thing is when you go back to that picture for 1 minute. So where it is in the room, like Karen's saying, really isn't important because it's in the room. So that window in that wall there, if you open that window, it's only coming in that one spot, but obviously the whole room gets full of fresh air. So it really doesn't matter where that duct is in the space. It's just got to be in the space.
The thing that might be more important is like thinking about where your supplies and your exhausts are, right? Because you don't really want both in one room, but if you had a room that had both, you'd want them opposite sides of the room so that you're drawing that air.
Well, that brings the point. There are some units I hear of once in a while. I think Panasonic makes a ERV or an HRV that is just one piece that goes in the bathroom. It looks like a bathroom fan, and literally, I mean, I'm not, their equipment's their equipment. If they're selling it, that's great. But in my view, the air comes in and goes right back out. It can't disperse because it's pulling out right next to, right at the same place as it's putting in. So it's going to short cycle air through the room in that case.
Yeah, good things to consider. As far as duct sizing goes, that's not something that we often see done per the, manual D for ventilation. Definitely for heating and cooling, we recommend it. But I'm just putting this out there that, the official way to size ducts, even for ventilation systems would be to use manual D. And it has a lot of great guidance just in general on selecting efficient fittings and duct sizes and equivalent duct sizes, which we'll get into a little bit. But these are sort of our recommendations to, figure out your duct sizes and select efficient fittings, limit your flex duct so you're keeping that static pressure low, seal all of the joints and the boots, and select registers for good throw, like I was talking about. This image here on the right, I included just to show how like a sharp throat or that interior bend of the elbow is actually the thing that causes a fitting to have poor flow. So it's creating this turbulence you can see in the image. So that's something really to look for when you're picking fittings. Probably, I'm guessing the cheaper fittings have like that 90-degree turn at the inside at the throat of the fitting, but it really is affecting your friction rate, which Mark will talk about here.
Right. Wherever you can use, like instead of a 90, if you can use 45-degree elbows, 45-degree elbows don't even count as an elbow. If you did two 45s to make a corner, that counts as straight pipe. So airflow is going to flow very freely. The other place to talk about it real quickly is a T. If you have a T in a system and you have a bullhead T, we call it, air is going to hit that and want to bounce back, and it creates a lot of turbulence. So if you have a T anywhere in your system, put a turning vane in, which is just taking that T that would be like that and putting a piece of sheet metal inside that comes to a point towards the airflow is coming into it, and it will split the air from that T. Much quieter, much better airflow using a turning vane. So think of it almost like water. If you're going to get a smooth flow, just like the air is going to, how do you make that happen? You look at all these fittings here on this chart. They all have they're all equated to a length of straight pipe. So if you look on the bottom here, this chart, look at the different fittings, and then you look at the on the left there, that's the static pressure, and it shows how many feet that those fittings are worth in a duct system. So the easiest one to talk about is a regular sheet metal elbow. It's in a normal system, a sheet metal elbow, the kind that adjusts a 90, that's equal to about 15 feet of ductwork. A T is equal to 30 feet of ductwork. So putting a lot of fittings in your system really makes it a lot longer. So you might have a very small area full of ductwork, but if it has 6 elbows and 2 T's in it, there's a lot of straight pipe measurement there, which can create a lot of friction for your fan. So the fans in your units have to be powerful enough to move the air through the duct system that you're designing. Because you may be picking a unit that's 100 CFM, and by the time your duct system is done, that unit might only move 50 CFM of air through that duct system because it doesn't have the power to overcome all the fittings you use. So another reason, as we talked about last week, to oversize your unit, always get a bigger unit than you think you need because of multiple reasons. Last week we talked about efficiency, we talked about being quiet. But another thing is that if you design this duct system or someone does it for you, you've chosen a 100 CFM unit because you need 100 CFM. You may get done and your final measurement is 50, 60, 80 CFM. If you have a larger unit that's adjustable, you can always turn up your fan speeds to overcome the duct system that you've created. So looking at this chart, there's lots of different things here. Most of these fittings aren't real common in ERV, HRV systems. Mostly we're talking about straight pipe and elbows in our systems, but just be aware that they do add up quickly when you start. If you call an elbow 15 feet, and then once again you get 4, 5, 6 elbows in there, that's a lot of pipe it's taken up. The other thing on the flex duct, I think we go to that next, do we, Karen?
Almost. I put this slide in there because I thought it was a great slide to demonstrate what Mark was just talking about with, the efficiency of the fittings. If you look, this was an analysis done by some students using some airflow software, analysis software. And you can see like with all of these sharp fittings and the bull nose T and the, straight 90s takeoffs all in a row, some of these registers, the air isn't even getting there. And you compare that to a system that really was designed for efficient distribution with all
With
of the
Ys
and sweeping elbows, and you can see how it really does a much better job of getting the air to where
and this
it's
is
meant
a
to go.
great place to throw in. Earlier you mentioned using dampers either at the outlet where you can adjust it or dampers in line in the duct. If you happen to end up with something like on the left and each of these runs have a damper in them, you can overcome the problems in that system by adjusting your dampers, because you're going to then be able to take areas where you're getting too much air and damper them off to force more air through the places that aren't getting air. So dampers or adjustable outlets are extremely important for balancing a system. Or you may, like in this system here on the left, you may end up with a couple of boxes or outlets that don't get any air, yet you're getting way too much through other ones. So that's extremely important.
Yeah, you'll probably end up with that in any case, right? But we also want to think about the efficiency of the motor, that's going to be working to push the air through these
Yeah.
complicated transitions.
So smooth duct, hard duct, we call it, the metal duct is always going to have better airflow than flexible duct. I mean, flex duct has its place. It's very easy to run. It is pre-insulated and people like to use it because it's quick and easy. What I would recommend if you're using flex duct, first of all, keep the runs short, keep it pulled tight. You can't have a flex duct that looks like a snake. It is horrible. It creates all kinds of friction. It doesn't allow for proper airflow. But if flex duct is used in limited quantities, pulled straight, it's fine used where it should be used. But I also recommend if your unit has a collar on it that will accept 6-inch or 8-inch, if you're using the 6-inch, stay with the hard pipe. If you're going to use some flex duct, move to the 8-inch size. Go to the largest size ductwork your collar will allow on your unit if you're using flexible duct. Showing these different shapes here of hard duct on the right. Also be aware that like a 6-inch round is not the same as a 6-inch oval, or a 5-inch round is not the same as a 5-inch oval. So it shows here, if you have a 6-inch round, you need to go to 8-inch oval or a 3x10 rectangle to get the same airflow that you have through a 6-inch round. So I've had people say, oh, I can't fit 6-inch round, I'm going to use oval. Well, that's great, but now your oval needs to be 8-inch and not 6-inch because it does have different airflow abilities. Excuse me. Here you can see about the flex duct. Obviously, there's ways to do it and there's ways not to do it. The picture on the top that we talked about, a snake, like a slinky, you don't want it to look like that. Airflow is going to be restricted. We talked about elbows being 15 feet. Well, essentially here in that piece, you have like 1, 2, 3 elbows, 4 elbows maybe in that very short piece of duct. And the inside of that is not smooth. It's got those that metal wire that runs through it, so it's bumpy on the inside like a corrugated pipe. So very bad airflow. And I see someone on the bottom say a short piece of flex makes a nice sound damper, and yes, it does 100%. I've had multiple jobs where you go to a duct system with an ERV, and for some reason, no one did anything wrong, but for some reason, that particular duct system is very noisy. It will sound like a musical instrument sort of thing. It just creates strange sounds and moans. And if not every single time I've ever had that happen, if you take at the unit, disconnect the hard pipe from the unit and put in whatever you can fit, 2 or 3 or 4 feet of insulated flex at the unit instead of the hard pipe, that sound goes away 100% every time. So in some people, some people are putting flex duct at the unit on every application. You can start there and put 2 or 3 feet of flex on every joint that goes into your unit, and then go to your hard pipe, and you will never have a noisy system that way. It's actually not a bad way to do it. But there is right ways and wrong ways to use flex duct. So obviously here, I see this a lot, this picture right in the middle. And whether it's on ERV, HRV, or heating and cooling systems, you see a lot of times they zip tie that inner tube, but they don't bring the insulation over, and they don't secure the insulation. That's definitely a problem. Looks to a very messy system. The one on the right, it's all good. It looks fine, but we have to be really careful. Like when you have straps, if you look at the bottom right piece of duct, it's hanging by a plastic strap. Where if you do that with a hard duct, it doesn't restrict it at all. With a flex duct, they can easily become restricted when you hang them with those plastic straps or metal straps. It can shut that duct down almost halfway going around the corner like that. So it's just something you have to be very aware of when you're using flex. It has to be done properly, or it should not be done at all. Pretty easy to spot good duct systems and bad duct systems right off the bat. I mean, I think the one on the left is actually a combination of hard pipe and flex, but it looks like a very good duct system. You have a lot of straight pipe. You have a lot of bends that are not sharp. They're kind of flowing bends. It's very good compared to the one on the right. Things disconnected, stuff not tied up properly, sharp corners.
I think there's a piece of gutter in there too.
There's a piece of what?
Downspout. There's a piece of downspout in there.
Oh, there probably is. Yeah. Yeah, there is. Yeah. It's unbelievable some of the things you'll come across places. But yeah, that you can easily tell a good system from a bad system just by walking in the room. Pretty much anybody can do that. You have to seal the ductwork, because if you're not sealing the ductwork, whether it's intake or exhaust, you don't really know where the air is going. So there's different ways to seal duct. You can use mastic, you can use mastic tape, you can use the metal tape. You do not want to use regular old duct tape. It just doesn't last. Regular old silver duct tape, yeah, it'll look great today when you leave the job, but 6, 8 months, 10 months, a few years later, it's gonna fall off. So we want to use a very high quality tape or the mastic sealant that you paint on. And it says right here, all duct seal, all joints with mastic as thick as a nickel. You want to have a good, tight seal, because once again, you don't want to be pushing fresh air into places that you don't want it to go, and you don't want to be taking air from places that you don't want it to go. And basically, because that's gonna make your system not have the proper airflow from where you need it from. So it's just not a good practice. Sealing is very important. Also seal the duct and boot to the wall or the ceiling, because like you can see the picture here on the right, that's got some, like, looks like spray foam or something around it. Because if you don't seal them, once again, you are pulling or pushing air into areas of the home above the ceiling or below the floor, places you don't necessarily want the air to go. You didn't figure in for that leakage, and it's just not a good thing to have. You want, like anything, pretend it's water, pretend it's going to leak. If you're doing air ducts, seal them like you would if it was going to be water, so you're not ruining anything.
I've seen this before a lot myself, where I go and I try to measure the ventilation at the terminal, and I see this big gap around between the drywall and the boot, and you can almost like see into the wall or into the attic through that gap. And I'm like, well, that's where all the air's going.
That's where all the air is coming from. We see it in regular HVAC systems too, where if the ductwork isn't sealed properly, and you're pushing a couple hundred CFM through some of these systems, a really small space that's not sealed, like on a duct that doesn't fit properly, you might have a 1/4 inch by 3 inch long gap. You can push, I don't know, 50 CFM through that. It's amazing how much air will leak through a hole in the ductwork that's not sealed. So very, very important.
This is a quote that actually somebody that I worked with told me, and I just wanted to note it because he said, if tested, they'll seal all of the joints of their system. Like normally they don't always seal everything, but if tested, they'll seal it. So maybe that would be a reason to tell your installer that you're actually going to be testing the system. So here's some examples of things you can do to help adjust that airflow and get the right amount to each area. I'm showing dampers and in the duct, and I'm showing all these are just basically comfort strategies, I guess. So supplying the air in a place that's not going to blow directly on people. So it could be high in a wall or in the ceiling, and using a diffuser that pushes that air against the wall or ceiling and not onto people. Adjusting the amount of air so it's not a ton in one area and almost nothing in another. And avoid that short cycling that we were talking about, the supply being too close to the return, trying to do strategies that will minimize the noise, and then finally testing the system and balancing the flows at the end. Here is a picture of a solution that can be used like either bathroom or kitchen intake actually, or return, where there's like just a simple, I think it's a MERV 3 filter that just fits up within the round duct and will catch a lot of that sort of dust and grease in the kitchen area. And it's also going to slow down your air a little bit, I guess. So that's something to consider. But they're pretty porous.
Just I'll throw in, and we talked about this in the last one too, is that we want to ventilate kitchens, but ERV, HRV it is not a kitchen exhaust fan. It can't go right over the stove. It can be in the kitchen, but not where you're cooking. And also, they are not makeup air for any kitchen appliance like a vent hood.
Yeah, we have a slide on that later on in the presentation, but I'm not actually sure we're going to get to it. So if not, we'll put that into part 3 and definitely do a deep dive into kitchen and bathroom ventilation.
Can you go back for one moment? The bottom, air temperature leaving the ventilator should be as warm as possible. Another, just a great reason to slightly oversize the unit, because a bigger core transfers to better heat recovery or energy recovery, which means warmer delivery temperatures.
Right, good point. So for diffusers, these are some options that I like that do that sort of bending of the air or deflecting the air. So it's like pushing it against the wall or the ceiling rather than onto people. And they're adjustable. They're very simple to install and pretty cost effective. They come in all different shapes and sizes and materials. Usually the plastics actually work better for adjusting than the metal. Obviously, like metal on metal isn't going to seal very well. And look for something that has a good sort of profile of the air distribution, so you know that it's going to provide comfort. And here's just a quick example of how you can use oval duct to put those registers high in the wall, bring them up from below. I see that done a lot. Mark, you want to talk about this?
Yeah, so these type of diffusers, the one on the left especially, I mean, it just, first of all, looks horrible in a wall. These are meant for HVAC systems. That's meant to be in a ceiling, and it is adjustable, but that is not one to use for a dedicated ERV, HRV system. It just doesn't look good. It's not the right application. The one on the right is just a return grill that would be for an HVAC system. Again, it's not adjustable. The fins are pointing in, right downwards, and it might be blowing on someone. We can't do anything about it. The round ones that she showed are much, much better for this type of an application.
And there are some rectangular ones out there, I think, that do adjust pretty well. Um, if you didn't like the round look or shape. But I don't have a picture of one of those in here, but it's definitely something that you might take a little bit more effort to look for.
Yeah. All right. So outdoor air intake and exhaust location. So the top right picture is a great situation where you have the intakes and exhausts up high. That's very rare to see because normally you're coming out the sill in the bottom of the house or near the sill, which would be in that white area, which obviously is too low to the ground for intake or exhaust. But Karen got this picture. The next picture down to the left is that metal pipe coming up and going out through. They actually did this, what, in a closet or under the kitchen cabinets or something like that?
Exactly.
Yeah, so that was how they got this high level on that particular home. We don't see that often. The one on the right bottom, you have to watch your intake because that one's clogged. That's actually from one of the islands out in the lake. Last spring, I saw that one. System's not working right. Well, all the vents in that house were clogged like that. And they can be clogged from a number of different things. The pollen in the air clogs them. You could, if you're mowing the lawn, they're too close to the bottom, they can get grass. In the fall, they can get leaves in them. If they're located near, if they're up high, even, I've seen a lot of them that are up high and they're too close to a light. So in the summer, they're acting like like a moth vacuum, and they get plugged with moths and all kinds of stuff. So that is another maintenance item, not only inside the house, but outside. Your vents need to be cleaned regularly. The goal is to keep these minimum 10 feet from a contamination source for your intake air. Your intake air is extremely important. You're bringing that air in the house. So when you think about contamination sources outdoors, we have to think about boiler or furnace events. We have to think about dryer exhaust. We have to think about range hood cooking exhaust, bathroom fan exhaust. We don't want our clean air coming in from anywhere that's not clean. You've got to be at least 10 feet from any contamination source. Think about things where if you're on a dirt road, you probably don't want it in the front of the house because you're going to suck dust into it. Think about if if you're in an area where neighbors or houses are closer, if you have a neighbor that smokes, you don't want to be on that side of the house because I've had that happen in a job that actually happened in my son's house. We put a ventilator in, and his next door neighbor is always out smoking, and the air movement from west to east was towards his house, so it was bringing cigarette smell into his house, even though it's supposed to be a fresh air vent. We don't want them over the driveway because if you're going to idle your car possibly in the winter to warm up a little bit, we don't want the exhaust coming in. You don't want it near your barbecue grill outside because you don't want to pull that smell into the house. So it can get a little bit difficult to find a clean area to bring fresh air in from, but that's extremely important. And also the snow line deal is extremely important. We have another picture later of an example where that wasn't done. So this is not always an easy thing. And it's not an easy thing to talk to a homeowner that's building a brand new home. We tell them we have to cut 2 6-inch or 2 8-inch holes in the side of their house somewhere. And they may right off the bat say, it can't go in the front. There's no way it can go in the front. Well, maybe the front is the only place where you can get fresh air because of other exhausts or whatever else, or the grade or whatever it is. So it is definitely something that needs to be talked about and taken into consideration. So next one. So this is the one, this is in Fairfax, Vermont. So those two hoods you see in the front of that house, they're way too low. They're way too close together. And obviously no one talked to me about this one before they installed it, and they did it. And they said, well, this is the only place we could get them. That's where it's going to be. Well, obviously this house also has a metal roof. So snow comes off that roof, buries these vents. The snow will be up to those windows in the winter sometimes. So now we have a hole around those two vents, 3 feet wide and 3 feet tall. And it just becomes a cavern for recirculation of air. So this does not work. If it was your own house or my own house, I'd keep it in mind, and I'd be like, I have to dig those out every time the roof sheds down. So I keep them free of snow. But either way, they're going to cross contaminate because they're just too close together. So beautiful house, brand new house, new installation. But once again, this is a place where it doesn't matter how far apart we could get them. There's really no way to get those above grade the way they should be in this application. It's a really tough spot.
This I included as kind of a positive example of a ideal layout. This was done by a mechanical engineer, but we don't often see designs like this done, but it just shows an example of a easily accessible location for the unit. The intake and the exhaust are not too long and they're 10 feet from each other. The ducts are sized, has efficient fittings shown and a fairly compact layout.
All right, existing homes. We have to do what we can do. In a new house application, well, it even depends on a new house. I'm involved in one right now in Waterville Valley, New Hampshire, where it's a big, big house. We're trying to do heating and air conditioning and ventilation. And the home is full of these LVL beams. They've got beams running every direction everywhere where you just can't get to things. So it makes it difficult. That's rare in new construction. Usually in new construction, you have a fairly clean path. In retrofit, you normally never have a clean path. You have to do what you can do. A few of these pictures here on the left side are actually from my sister's house when I helped her put a system in. We were just installing this. It's not complete in this case, but unit went in the basement. And so I guess I'll go back a little bit. So we want to get fresh air in all the bedrooms and take air out of the bathrooms and all that. Well, you normally cannot even consider doing that in a retrofit. There's just no way to do it. So in this particular house, it's an older house with a lot of small rooms. Said, what the heck can we do? There's really no attic because it's a Cape style house with a finished upstairs and the basement's finished. So what can we do? We got to put a ventilator in. So put it in the basement in the mechanical room. As you can see on the left, that's up through a first floor closet going up to the master bedroom upstairs. This terminates under the bed in the master bedroom. The outgoing air we took out of the finished basement just outside the mechanical room wall. So what essentially happens in this house, fresh air comes in and goes upstairs to the second floor under the master bed, moves through the master bedroom, down the hallway, past the bathroom, down the stairs, probably kind of splits at the bottom of the stairs going through the dining room and the family room, eventually goes back to the kitchen, down the stairs, through the finished basement, and out the wall to outside. So it works really, really well. There's a couple of bedrooms we weren't able to get to. There's just absolutely no way to do it in this house. At the particular time, her kids are moved out. Master bedroom's fresh, hallway's fresh, living space is all done. They're very, very happy with it. It ventilates the house extremely well. In fact, she says when it's not on, she can tell almost immediately that it's not on because she's so used to having the fresh air in the house. So, Karen, is the one on the right your house, you said?
Yeah, that was my house. I just wanted to show an example of like taking out some of the previously finished room space and building out an additional chase. So there's going to be at the time there was about to be a chase built around these ducts that you're seeing next to the fireplace. And that was like the only place that we could find to bring it up from the basement to the second floor, but it ended up working pretty well. I kind of wish the ductwork was a little less convoluted and more straight and better airflow to the second floor, but that's why I put compromises here at the top.
Right. There's always compromises in a retrofit. There's always compromises. You're either going to lose some space in a room, you're going to lose some space in the closet, in the cabinet. You have to make a sacrifice somewhere to get ventilation into a new house. So this is an interesting job here. I sent Karen some pictures the other day. This is actually in Marshfield, Vermont. There's a school that didn't have any ventilation at all, and this was during COVID, and they want to get ventilation so they could open back up. So these units were actually installed in multiple areas around the school, All the ductwork is exposed, but it did the job. We got it done. The school has fresh air. They're very happy with it. The systems are very, very quiet. Um, again, compromises. You can see these units in the school. They're all over the place, but they wanted to reopen during the COVID, and we got it finished, and it's working very well. So I don't remember the name of the school, but as you're leaving East Montpelier, it's on the right-hand side, the outside of the building there, you can see. This actually here, this is another job that's actually in Marshfield, Cabot, right there. It's a church. Again, during COVID, wanted ventilation, exposed ductwork in the church, air so the picture on the left is fresh air coming in because it's right over the people, and this picture on the right is at the back behind the piano, behind all the chairs, against the wall where the kitchen area is. And we're taking air out there, so we're bringing fresh air in across the people and bringing it back toward the back of the church. And once again, this is an application that worked out really well, and it doesn't really look that bad. Even all this exposed duct, after you see it a couple of times, it looks fine. But a pretty neat application.
Okay, we got about what do we have? 22 minutes left. And we've got a couple of sections to go through. If we don't make it through all of this, we'll move the last part to part 3. But wanted to get into some controls information here. I'll let Mark handle this one.
So controls, I'll go through quickly. I touched on that earlier. Lots of ways to control it. You can do intermittent operation. You can do constant low speed. You can do constant low speed with a boost. You can do CO2, humidity, motion sensing, all sorts of things. In general, for a house, in general, either intermittent operation or constant low speed with a boost is the best way to do it. CO2 sensors are great for applications, again, where we have a lot of people, but a lot of times a CO2 sensor will not ventilate a home enough because we don't always have high CO2 levels. Motion sensors are great too, but a motion sensor, people will say, I want one in the bathroom. Well, my problem with that is that if you don't go in the bathroom, it doesn't come on, right? Or you could boost it with that, but even if you're boosting it in the bathroom, so if I just run downstairs right now, run in the bathroom, I get a Kleenex and run back out, well, I hit the motion sensor, it's going to run for 20 minutes. So it's not a great application. So if you got questions on controls for a specific application, give us a call and we'll talk about the different ways to do it and what would be best for your particular job.
Sorry, I didn't mean to jump the slide there.
No, that's fine.
I guess we'll go on.
Yeah, I mean, the controls are job by job. We can go through 100 scenarios. So again, if you have questions, contact me directly, contact Karen. We can walk you through a job for sure.
So for commissioning, what we're really talking about is testing and balancing the system. So often I see these systems, like the unit is installed, the ducts are connected, and then everybody is off the site and nobody's actually gone through the manufacturer's instructions for startup and balancing the unit itself. So there are also aspects of the code that actually are requiring you to test the system. If you were there for part 1, you will remember that most of the airflow calculations that we looked at actually required verification. There was only one that didn't. So the things that the code allows you to use for that are included on this slide. Probably the least expensive would be like this black box like we're showing here, which you would connect a manometer to. So you can either test at the exterior intake and exhaust. You could test at the unit itself if it has ports for testing, or you could put your own locations in the duct to use a static pressure probe to test the airflow with a manometer. The ones that we use at Efficiency Vermont are this, excuse me, this is a RetroTech flow finder that I have in the red box here. And it's known for having very accurate measurements at low flows. So we like to use it for testing at the registers themselves, at the diffusers, because we can then balance the system with those numbers. I'm going to move on. So just things to know at the ventilator. Again, follow the manufacturer's instructions for startup. Right. test the airflows at the ventilator and balance the system, if possible, at the ventilator itself so that they're within 10% of each other. That's considered balanced. I think, honestly, 0% is the best. People have different thoughts about that, but and then this is where you want to set the program the machine in the way that you want it to run, or was
The key is
designed.
the key thing you said is always follow the instructions of the manufacturer. They're
Yeah.
all different.
Yeah. And then for the rooms themselves, that's not required by code, but we definitely highly encourage it. And if you are a member of the EEN and building a new home, this is something that we offer our EEN members. Is we have the equipment, we can come out and test your system and help balance like it room by room. But it's kind of a time consuming process. It really involves going around to every single room and testing and writing down the numbers and then adjusting things and testing again. It could be quite a few rounds before you finally got it efficiently, equally distributed between rooms. And there's all kinds of issues that I've found when testing at the register, like all kinds of issues. So I really highly recommend you at least ensure that there's airflow at each register.
All right, so this is a real job here, believe it or not. This was a multi-family housing job in Dover, New Hampshire. And I got a call that the units, since the balancing people came in, the units were too noisy. Well, I got there and this is how they balanced the airflow. So you see on the left, that's one of the air intakes, and they have it closed off. Like I'd call that 95% of it is blocked off by a piece of metal. And the airflow going out of the units was done with tape on the side like that. So I don't know who the heck did this, but this is not the right way to do it. This is a very poor job, whoever did this, and this is not the way to change airflow in a system. They ordered single speed units. This could have been avoided if they had variable speed units. We could have adjusted them wherever they needed them, but they ordered single speed units that were obviously way too big for what they wanted. And this is how they decided to balance it. So, long story short, this all was removed. They're operating at their full capacity, how they should operate as a single speed unit. And this balancing stuff was all thrown out the door because it just was ridiculous. But it's amazing what you'll find out there.
All right, we're going to quickly go through as much maintenance and troubleshooting as we have time for, and maybe leave the last 10 minutes for questions. But we'll see what we can get through. Yeah,
So
I think
maintenance basically on an ERV, you're going to change the filters. If the filters get extremely dirty or compromised or are removed and the core gets dirty, you are going to vacuum the core off of an ERV with a soft bristle brush. The material is, like I said, it's a hygroscopic resin material. It's not fragile, but it's definitely not really tough either. It is a damageable material. But if the filters are on, these cores are going to last for 25 years if you keep the filters clean. Other way to go in an HRV, if you have an HRV that has the metal or the plastic core, you can actually remove those cores, take them outside and wash them with a hose. So that is one advantage to the HRV is the core is easier to clean. But in either case, the core should never really get dirty if the machines are maintained properly. Also, the outdoor vents, as we talked about, that's another one in that same house I showed you from earlier. Completely plugged. Most of that's tree pollen. That was in the spring. That's a lot of that the white cottonwood or something that's
cottonwood,
all
yeah.
floating seeds in the spring gets full of that. But also, again, they'll get full of leaves on the suction, grass clippings, bugs. They do need to be maintained.
And vacuumed, right? Last time you were saying
Yeah.
that they should be vacuumed rather than just sweeping it off with your hand, which is what I typically do
Well,
because it just
because
gets
yeah, so
sucked in.
if that's an intake and we blow it off or wipe it off, it's all that's going to get sucked right in by the machine into the house. But if you vacuum it off and pull it back out the way it went in, we're not going to do that. Generally, the exhaust ones are generally not as dirty because we're exhausting out of the house. Rather, we're not pulling in leaves and junk like that from interior of the house. But yeah, the intakes definitely need to be cleaned. And again, two things here to think about. So if they're too close to the ground, as we said, you're going to get that leaves, grass clippings, and all that. If they're up high and they're near a light, they can suck in bugs. But also, if they're up high, someone's not going to want to go on a ladder and clean them. So it really should be somewhere that's easily accessed so that people will clean them. Because if, again, no one's going to carry a vacuum up to the 30 feet high on the backside of a house because they're dirty. It's going to be a difficult situation there. So it is something to consider also. So troubleshooting, this is a job that I went to. So what's happening here on the right-hand side is that, so you can see this duct on the left. This is a warm, humid day. This is a moist, humid basement. We've got this day out, it's a cool day outside. Let's say it's 50 degrees outside and it's a very warm, humid basement. So on this day, that duct is getting wet, just like your can of soda or beer would when you took it out of the fridge on a humid day. It's going to get wet. Just what happens. What happens in the winter on the incoming line is that we are getting that happening, but it's freezing. So it's turning that into a popsicle. That's why that these ducts on the incoming line especially have to be very well insulated and sealed. You can see by this guy's hand, actually it's my hand there, I'm pulling the insulation back, exposing that frozen pipe. The pipe is insulated. Yes, it was insulated, but it was not sealed on the two ends. So insulating it and allowing air to get in under the insulation, this can still happen because what you're seeing here on the left is still happening. It's just freezing because the interior of the pipe is below freezing outside. So it has to be insulated, sealed on both ends, basically airtight so that no air from that humid basement can get to it. And this will happen on any job where there is moisture in the house. So if it's a humid basement, humid crawl space, if it's not done properly, you will have a mess. And this becomes a big mess when that thaws out and starts dripping. The insulation sags, starts dripping. As an installer or a manufacturer, you're going to get the call, someone saying, your unit is spilling water all over our basement. And it's really not the unit, no matter what unit it is. This is a science project. This is not a unit malfunctioning. This is a improper installation. And that's what's going to happen. This is an ERV core that's gotten wet. As I said, you cannot wash the ERV core. You can only vacuum them off. The material, if it is wet too often, it will shrink. Basically, what it acts like is like a sponge. So if you go to the store and you buy a brand new sponge today for your kitchen dishes, take it out of the package. It's all soft and nice and works great. You wash the dishes on, you put it on the counter. Tomorrow morning you get up, that sponge is shrunk up and it's hard as a rock. That's what will happen to an ERV core if it gets wet. It will shrink and it will get hard and brittle. And now you are not passing air through the core. You're passing it mostly through these open voids in the system. This one here is a system that's actually a commercial unit, multi-core unit that is at a brewery. And the people in the brewery were washing the units out. And this is what happened.
I'm just going to take a pause here to see, we have a couple more slides to go through, which we can do if we have time, but I also wanted to see if there are any questions and take those before we end.
I'm not seeing any questions at the moment, but if anyone would like to ask a question, feel free to use the raise hand feature on the toolbar on the bottom of your screen. You can raise your hand and I can unmute you and you can ask your question or just put it in the chat.
Cool. Yeah, so that's what happens when an ERV core gets wet. And the issue here is that the core can be changed, but the core is usually like 75% of the cost of the whole machine. So next slide, troubleshooting. Well, the one on the right we'll talk about first. So that's the one that we showed earlier that someone put up a sheetrock wall in front of it that we can't open. So how are we going to service that unit? That becomes a big problem. Also looking at the top of that ductwork is not sealed. We just talked about sealing the duct to the unit or to the collar. That flexible duct right there is not sealed to that collar. So if that is the air intake and it's humid in that house, we're going to get icing on that, just like we did in that other picture. The one on the left was a really difficult troubleshoot I went on. This was in Stowe, and I got a call from the contractor. He installed the unit. He said, I put this unit in a couple months ago. It's been working great. Now the people called and they said the windows are all wet in the house. They got towels on all the window sills. So I said, all right, I'm going to be in the area tomorrow morning. Let's go check it out. So we got there, and it was the windows were actually running water down like someone had squirted them with a hose. It was like 78% humidity in this house in the middle of winter. And went and looked at the unit, and we found the very difficult troubleshooting here. It was unplugged. One of the people's fathers had come to stay with them for a few weeks. He saw the unit, didn't know what it was, thought it was a waste of energy running it, so he unplugged it. And 2 days later, they're living in a terrarium, and plugged it back in. And within 24 hours, everything was back to 30% humidity and functioning beautifully. So troubleshooting can be really easy, or it can be more difficult. Duct system troubleshooting. This is what we talked about earlier. If you see these duct systems, you know instantaneously this is not a good duct system. All kinds of issues and problems here. Just no reason to talk about that one any further. Just you can tell instantly we have some major problems going on here with this duct system. And good duct systems, short, clean, insulated, sealed with foam, mastic sealant, that you couldn't have a better job. These are extremely well done systems. Very easy to tell the difference right off the bat. Some more nice systems here. In fact, this brings up something. The system on the left here, actually, this was a job that is not too far from where I live here in New Hampshire. That a few years ago, I got a call on that job when he was done that the system was too loud. This is one of the ones, for some reason, that duct system was having some strange noises moaning through that duct system. It was very weird. So we went there, took out on the left-hand side those two hard elbows, top and bottom. Those are the two ones going to the interior of the home. To put about 3 feet of flex to replace those elbows, and the system was absolutely 100% silent. Nothing changed except that hard duct was decoupled from the unit, and it was very, very quiet. One on the right, just a classic, really good looking install. Kitchen ventilation.
Yeah, I didn't think we'd get to this. We got 5 minutes left. So yeah, what we were saying before was really you should consider having a dedicated kitchen ventilation system. There is kind of like a current um, line of thinking that any additional penetrations in the wall and the exterior wall of the home is not a valuable thing. So was a period of time that we were seeing a lot of recirculation hoods with a pickup for that, tied into the ERV system 6 feet or more from the range or the cooktop. But we're finding that, there are a lot of fumes and VOCs and, particulates that are created with cooking, and it really is a good idea to exhaust those directly to outside. So that's currently what we're recommending. On the next slide, there's actually a guidance document link that can take you to some more information about kitchen ventilation. I've seen some, like I was showing before with the cone filters, that's a good type of filter to put in your ERV pickup 6 feet from the range. There's also these louvers that have a hinged door that just take like a simple rectangular filter that you can change. Some of them, I guess, you could wash. But yeah, is there anything else you want to add to that?
Yeah, you definitely. So if you have a kitchen range hood, I mean, you're talking in this thing here, 200 CFM. Well, I'm regularly seeing in new construction 6, 8,000 CFM. That's a lot of air. You have to have makeup air for that. You're gonna pull a vacuum on the house. Someone's gonna spend thousands of dollars on a big hood over their 8 burner stove, right? And it is not going to work. You're going to turn it on. It's going to suck a vacuum on the house within 10 seconds, and it will not ventilate. You need makeup air. An ERV or an HRV is not makeup air, period. They don't do that. I've had people argue, well, you can offset it and bring more air in than you take out. The manufacturer I work with allows 10% variance. So on a 100 CFM unit, you could bring in 10 CFM more than you're exhausting. But if you have 1,000 CFM makeup air hood, that does absolutely nothing. That's ridiculous. So anything over 400 CFM by code has to have makeup air. But if it's a very tight house, I would say any kitchen exhaust hood needs some type of makeup air. We do offer heated makeup air for kitchen exhaust applications. It's very important. And just real quickly too, I'm a big fan of propane stoves. I like to cook a lot. I love cooking with the fire. But if I run my CO2 monitor in my kitchen, when I turn my stove on, especially the oven, I just did it the other day again. I even had the doors open. I had the kitchen door open and the front door open in the house. I was at 500 ppm of CO2 in the kitchen. I turned the oven on. Within 5 minutes, my CO2 level in the kitchen was over 2,000 parts. Propane stoves put a lot of CO2 in the air. So that's a big reason to ventilate. And that's my argument for people wanting to fall asleep on Thanksgiving after they ate turkey, saying they ate too much turkey, they're falling asleep. I say it's complete baloney. You've been in a house that the oven's been running all day long with 10 other people, and the place is loaded with CO2. That's why you're sleepy. So, again, kitchen ventilation, whole nother subject, but I can help you out with that if you have any questions.
Yeah, I was going to say, reach out to us if you have further questions about kitchen ventilation. These are just some guidance documents that Efficiency Vermont has on their website, which you can get to through these links. And the Energy Code Assistance Center is another place to reach out to. I think Alex put the link to that in the chat.
And look at that, it's exactly 10.
Contact information. Great.
Exactly 10.
So we did it. 1 minute for questions if there are any. Otherwise, I guess we can wrap it up.
Yeah, wow, great job, both of you. That was fantastic and very entertaining. I'm not seeing anything come in. Give it a little bit here. Some folks are saying thank you.
Good. Feel free to contact us. Feel free to contact us, or ask now. I mean, anything you want to talk about with ventilation at all, or HVAC related, just give me a call. I'd be happy to talk with anybody.
And oh, we looks like we got our hand raised. Apologies. Let's see. All right, Ethan, you are now able to come off mute.
Hey, apologies. Did not mean to hit the raise hand button, but thank you so much. This was a great presentation.
Good,
Glad
thank you.
Enjoyed it.
Thank you. Oops. Sorry, Gio, I just clicked on your name too, so you can unmute if you wanted to as well. My apologies. But otherwise, I believe we'll be posting the registration link for part 3 of this training in October here very soon, if it is not up already. I linked our upcoming trainings webpage. If you scroll up to the top of the chat, you can find it up there. This training is being recorded, and we'll be able to post this on our recordings website too, which is also linked up top in the chat. And hopefully we'll have part 1 of the recording out soon as well. I'm not seeing any questions. So,
all right. Everybody have a good day.
Okay.
Hey, sorry, you know what? Hey, if you're still there, looks like I missed it. Okay, the one question I did want to throw out is about monitoring. Sounds like Mark's got a CO2 monitor in his kitchen, and I guess, I've run some AirThings wave monitors in my own house and some projects, and and then you got to stay on top of those, and sort of over time. I don't have a sophisticated monitoring system, so I am curious about what kind of monitoring for indoor air quality is taking place, because more data would be helpful, I think, in convincing reluctant homeowners to install proper systems and remove CO2 stove or propane stoves, things like that.
Right. I think it's kind of hard to enforce something like that, but it is something that homeowners do on their own. And I find that anyone that does take the initiative to get some type of indoor air quality monitoring devices in their house, they find out that they need a lot more ventilation than they thought they did, if you really want to have a clean indoor environment.
Efficiency Vermont has done a lot of monitoring, and there's actually a white paper out there about the results of a test study that looked at exhaust-only ventilation and then balanced ventilation, and it's really, really interesting. And this is a lot of the reason why we're seeing balanced ventilation come as a requirement now. And I can find that link and share it with you.
Yeah, exhaust-only ventilation. We talked about that in other presentations we've done, where the problem is you don't know where the air is coming from. And a lot of times the air is coming from like a basement or a garage. And a lot of times exhaust only ventilation can make the air quality in the living space of the house worse by bringing more radon upstairs than we had. More chemicals that we store in the garage and basement are now being dragged through the house. So it's an interesting subject of monitoring and how to monitor it. But I think as people learn more about it and the public becomes more educated, and they do some testing on their own, they're going to find that the indoor air quality in people's homes and in workplaces is much worse than people think it is.
That's what I have heard and found. And certainly, energy use is something people can see on an annual basis and when they're building high performance homes.
Right.
But I think it would be really useful if we found ways to more easily see and measure, make it even more visible to our customers. Yeah.
Right. The easiest one to use is and the cheapest monitor to get is the CO2 monitor.
Yeah.
So you can use that. I don't know what your position is, but if you're with a homeowner and they're talking about putting in a ventilation system and you meet them in their home and you go in their kitchen, maybe sit at the kitchen table, and if you just turn on that CO2 detector while you're there at the kitchen table, you're going to see it going up and up just from the 3 or 4 of you talking to each other. And if you really want to get it going, like you said, if they have a gas range, ask them, hey, could you boil some water for me? I'd like to have a cup of tea or something. And you'll see that monitor just skyrocket. It'll be amazing how fast it goes up when that stove comes on.
Yeah.
Another thing with stoves is I shadowed our colleague Steve Spatz on a site visit where we tested someone's oven, and I think the ppm got up to about 1,800 while the stove was starting up. But Steve also recommends you can get your stoves tuned so they burn more efficiently rather than you can kind of save and not emit as much CO2. So some tuning would work as well.
I think you might be able to do that, but I think in general for the general consensus of the public and as time goes on, people are not going to do that as a regular thing.
That's right. I mean, the first time Steve brought that up, I never even knew.
I never really had anyone do that either. But like just said, that's a great thing. It's like people don't keep their filters changed or their car oil changed properly. Having them have their cook stove serviced and tuned up, I think, is just that's not probably going to happen. But it's a good idea, but it's just probably not going to happen.
Thanks, you guys. Appreciate it.
All right. Thank you very much.
Thank you all. I don't see any other questions, so I think we can wrap it up here.
All right.
Sounds good.
Thank you.
Thank you all. Have a great day.
You
Have
too.
a great day. Bye.